why this lab exists and the department that it's within. We have 6 concentrations in the aerospace department, one of which is aerospace technology. Aerospace technology has been historically as close as we could get at MTSU to an aerospace engineering type undergraduate degree. Since we can't call it that, all these students are given the courses which have pretty much the same core as you guys have in mechatronics, if most of you are mechatronics students. Same engineering core, a really good math foundation up through differential equations, good physics, good computer science, and then I have my students, it's a recommendation, either double major in math or physics, and then they go off to grad school in either mechanical or aerospace engineering typically. So that's what we do. And this laboratory is funded by grants to allow them to do research in their senior year. So they have a course called Problems in Aerospace in which they do research, typically working on a project that I have streams of research going on, and they join that and do their own independent pieces of it. So all of this is student research equipment. We have things over here. One of the projects that's going on right now, actually with Danielle, is a study where for about 3 years now, we've had a sound study where we've taken small UAS or drone propellers and rotors, measured the thrust, measured the sound, modified the props in certain ways, measured the thrust and sound again to try to make them quieter. Because it's now legal to operate drones in the US up to 400 feet AGL, under 55 pounds with a remote pilot certificate for money, but they didn't limit, the FAA did not limit the noise that they make. So there's no requirement. Yeah, but since they're low and they're loud and they're gonna be more of them as the years go by, they could fly over your house and your commercial areas. And for sound, there's no regulation. So we are attacking the sound of these small things, and we've done it on small thrust stands. This is a little thrust stand. We've got other thrust stands around the room I'll point out when we come by them. But we've moved to, in the last year, actually doing flight testing of these things. So this semester, and you can talk to Danielle about it afterwards for what she's actually doing, but these things are hovered at 4 feet, 8 feet, as high as we can get in the space. We measure the sound with different little sound pressure level meters. We know what the thrust has to be because we know how much these things weigh. So you don't have a thrust stand when you're flight testing it. We just use the weight as our nominal thrust value divided by 4 for the 4 props. But we know we can measure the sound. So we're quantifying that. And these little props, the ones I held up, are by the manufacturer, they're quiet props. So last year they released a quiet prop, which is slightly quieter. And then Danielle is applying modifications to the quiet props to see if we can reduce the noise even more beyond what the quiet prop does on its own. So there's some device we have. This is one of the sound pressure level meters that we can use. This is just a newer one that we've tried out. We've got another sound pressure level meter. I don't know, Danielle, where the little one, oh, it's standing on a mic. Yeah, there's one right there beside that little metal platform. So those are things we use. We've got one of the biggest test devices, and you guys can roll over here and look at this one. This one, it's been a bit since we've used it, but this is a really common fluid mechanics tool for both visualizing what flows do, but also for measuring forces and moments created by flows on bodies. Wings, boats, cars, whatever you're talking about, you can immerse it in a fluid, in this case a water tunnel. So we'd fill this up to about right here. There's a pump beneath the table on that end, just a little impeller pump that's going to force water up underneath that perforated cylinder over there. The water then flows out. It comes through all of those little tubes, which are really basically just plastic straws all connected together. So it forms a bit like a honeycomb that straightens all the fluid out. So you should have pretty good laminar straight flow coming through that, and it's really slow, which helps. And then the flow comes through this restriction. And one of the equations you guys have studied at this point is known as the continuity equation. And it says that when the area of a flow comes down, what should the velocity of the flow do if it's an incompressible fluid? Speed up. So we get a little bit faster flow in this restricted passage. We have a model that sits in here mounted to some sort of device, and we can either inject dye with a little dye wand, and we can see what the fluid does when it flows over something, or we can mount a force balance here and suspend a model similar to this one in the flow and measure things like lift or drag, moments if we had a force balance so equipped. This is a student-built test article. It's been a couple of years ago. This little article was meant to see what happens with rotating cylinders in a shape. So you guys maybe have studied Magnus effect in fluid mechanics. I'm not sure if you guys have
not
got
yet. Yeah.
Okay.
That's
So
what we get into now.
flow over a cylinder. So what this little pipe was a cylinder before we cut it in half and mounted these other cylinders on the back of it. And so what you can see in this and measure is that fluid is going to separate from the backside of a cylinder in an oscillatory way. And it's called a Kármán vortex streak. You see these little eddies that alternate top and bottom. And there's drag there, and it's oscillatory lift as well. But if you have these rotating cylinders, that's going to drag the fluid behind the body just due to friction, the no-slip boundary condition, and it will reduce the drag and cut down on some of the oscillatory flow separation. So that was the test of this. And then the water flows through here. It goes back through these drain tubes. It's sucked in a circuit along the bottom where it's just recirculated through the tunnel. So a water tunnel, a very common flow device. My dissertation research was done in a much bigger water tunnel at the University of Tennessee Space Institute. So this is our smaller scale tunnel. If we flow over this way, this next device right here is a wind tunnel. So it does the same thing. You've got a honeycomb type filter up front, which just straightens the air out as it enters. You've got a flow restriction. If you look top down, the area gets really small. It's only about 2 inches across inside the cross section. So you speed fluid up just through continuity, and then it exits out the back. So this is an open circuit wind tunnel, where that's more of a closed circuit tunnel over there because the water's recirculated. You can put little things like airfoils in here, and I think what we've got in this now is a delta wing. So if you're familiar with the Space Shuttle Orbiter that we don't use anymore, or the Concorde that we don't use anymore, and some other aircraft, most of them we don't use anymore, they've got big delta wings on the back. So the wing looks like the Greek letter capital Delta from the top. There's a delta wing looking down at it from the top. And if you can see, it's angled the nose up. So this is a wing with what we'd call a positive angle of attack. We're looking top down at it. And we could blow air over that, and there's nothing special about blowing air over that because we can't see it. But tunnels allow us to visualize. So we've got a little water tank down here. We'll draw a vacuum, we'll vaporize some of that water, and then it'll come out of these little rakes, and you'll start to see streamlines or paths that molecules will follow. So those are streamlines over that thing. And one of the things you can see is, you see it kind of rolling up here and rolling up there. So when you've got a lifting body in a fluid, that means there's a higher pressure on one side, the bottom, than the lower pressure on the top side that we're looking at more directly. And high and low are going to equalize, and it can do that around the wing tip. So you've got a high pressure bottom wrapping to the low pressure on the top, which sets up that little vortex known as a wingtip vortex. You've got two of those. Anytime you've got a pressure differential, you can have a vortex. So anytime something is lifting, you've got a pressure differential, you've got a vortex, as long as you've got a tip. And so that's just kind of a cool thing you can do in a fluid tunnel. And we've got different models that we put in there, little airfoil models, wing models, so you can change the angle and see what happens to the streamlines as it flows over it. We can even connect models to suction or pressure. And so this little model has holes, it's perforated. So we can either draw a vacuum through that, or we can expel air from it and see what that does to the flow around the body. So we can see those modifications here in a device like this. This one, if we move over, is our biggest wind tunnel. So this is a borderline educational wind tunnel to a pretty good data collecting wind tunnel. This one has the big inlet down there, and again, you can see the honeycomb for flow straightening as the flow comes in. You get pretty smooth flow in here. You can again see that big restriction. So whatever the area of this, it's about 4 feet by 4 feet, 3 to 4 feet. It goes down to 1 foot by 1 foot. So you have upwards of a 16-to-1 restriction in the area. So we can get speeds with that restriction and with the strength of the big electric motor that drives the fan to pull the air. We can get speeds of around 100 miles an hour right here in the test section. But the speed is not the most important thing. I think you guys have probably talked about Reynolds number. Mm-hmm. That's the important thing. So given the size of the object and given the speed that we can draw here, and the density of the air in the room, viscosity of the air in the room, we can get a Reynolds number. And that's really what we target when we do fluid testing, is what's the Reynolds number that we're actually testing. This is a device back here that holds the model, what we couldn't see in the water tunnel we've got here. This thing is known as a sting. And although it doesn't sing Roxanne, it can hold on to a little wing model like this. And when this thing experiences a force, it just passes through the sting into strain gauges that then turn that electrical signal into a force that's been calibrated. So with this thing, we can measure lift, drag, and a pitching moment, an aerodynamic pitching moment on the wings. So we can vary what we put in here, wings, complete airplanes, different things on that shelf, drag models we can put in here, or experimental things that we create with our 3D printers over here. We can install those in the wind tunnel and measure speed. Now this tunnel is pretty old. It's over 20 years old at this point, about 23 years old. And when I came, it was all analog. And so we updated it with a digital system. So it's got a National Instruments data acquisition system flowing through this desktop PC that displays on a screen on the other side, but it started to die. So some of the DAC cards inside, I think, have died. So first, I lost airspeed. So I couldn't measure my airspeed in the tunnel, which is pretty important for getting things like Reynolds number, for knowing what your forces and coefficients are going to be. So I really quickly constructed a YouTube manometer, which you guys may or may not have discussed in fluid mechanics. So this is a simple device. You've got a pitot end, you've got a static end. You insert it into the tunnel up through this little flexible membrane that comes up right here, and we can measure speed again. So just get the YouTube manometer reading, calculate speed, and we're good to go again. But we have since also lost forces, and so now it's useless. So until we get this repaired, we can't do much useful work with it. Moving around, we've got a couple 3D printers that students can draw things on, or draw things and then upload it, and we can get test articles, whether for the wind or the water tunnels. All this foam is for a little experimental thing we did a couple of years ago. Did anybody hear about Red Bull Flugtag when it came to Nashville 2 years ago, I think in 2017? So Red Bull Flugtag, Red Bull is actually pretty big in aviation. They've got the Red Bull Air Races, which are being canceled. They've got Red Bull Paper Wings, which has come to MTSU twice in the last probably 7 years. That's a paper airplane contest. And we held it at the airport in one of our hangars just this last year, where it's a worldwide thing. You build paper airplanes, you can either compete for distance or for acrobatics or for endurance. And the winners locally go to the worldwide competition that's held somewhere else, Austria or somewhere. And so we've hosted a couple of those. Well, they also do something called Red Bull Flugtag. They do it every year, where people build big gliders that somebody's actually going to sit on, and the team pushes them off of a dock or a pier that's about 20 or 30 feet above a body of water, and they see what happens. So in 2017, Fermentation Science was a brand new program on campus. They had put in a bid to compete, because it's a lottery system. You apply and then they draw who the competitors are going to be, 40 for the whole Nashville area. And Fermentation Science, along with their industry partner, were selected. But they make beer and wine. So they reached out to Aerospace and said, hey, will you help us with this? So myself and a couple of my students said, yeah, we'll help you. So we designed and built a glider in probably about a week, because it was so close to the deadline when we got started. These are the leftover foam bits that form the core of the glider. So these big chunks of foam down here, just insulation foam, you can get at Lowe's or Home Depot. We took this as our core material that we shaped with hot wire foam cutters. We laid over it fiberglass and or carbon fiber to give it strength. So we made a tandem wing / canard style glider that I sat on, and the team pushed me off of a dock about 30 feet up over the Cumberland River in Nashville, August of 2017. It was an interesting experience because as you design something, the center of gravity is pretty important for an airplane, for sure, where the CG is going to be. And I had a design point for CG, which is really where I sat, because I'm driving the CG. The glider weighed maybe 40 pounds, but I'm the majority of that, of the glider when I add my weight to it. So my position was specific, but on the day of the competition, the safety people came around and said, no, you can't sit there. You've got to sit back here, because this is not usually an aviation competition. It's a silly thing where people design whatever that looks crazy. Somebody sits on it, but as soon as it leaves the dock, the person bails out and jumps off and just flops into the water, and the thing kind of crumples up into the water. But I designed it to fly, and I was going to ride it to a safe landing somewhere. So when they told me I couldn't sit there, my CG was too far back, and as soon as I left the ramp, my nose pitched up, and I pushed forward. I actually cut little footholds so I could push forward because I knew it was going to happen, but I pushed forward. It's too late because my nose is already up, and my head had extended past the nose of the glider at that point when I'm trying to save it like a ski jumper. And so I saw the river coming up to punch me in the face, and it blacked one of my eyes. I felt like water injected into my skull on one side. So these are the remnants. So it comes about every 10 years to Nashville, it seems like. It's come twice. In about 8 more years, it might be showing up again. So if you're interested in doing something like that, then keep your eyes open for Red Bull Fluke Talk. But they do it all over the country. This is one of the little test stations for sound testing. So here are the little microphone or the sound pressure level meters that Danielle is using, those type. This is a little bitty thrust stand that we use to do propeller testing as well. And also I teach camps, high school camps that come through here in the summer, and we do propeller testing. And this is one of the little thrust stands that we spin the props up with. This is, if anybody's a gamer, this is probably the best laptop I've ever had my hands on. So this is an Area 51 Alienware laptop, new as of this past summer. It's an awesome computer. It's crazy fast, super heavy. It's got 2 power adapters to actually keep it running. But we've loaded computational fluid dynamics software up on it. So we do CFD, digital wind tunnel stuff on it. So we're doing it with that just to see if it's as good as this computer right here. So we've got 3 big CFD machines, those 2 and this one. This is the newest of the big workstation PCs that we have. We run code on these called Stallion 3D, which is a fairly accessible CFD machine, running upwards of pretty good Navier-Stokes equations, if you're familiar with those equations from fluid mechanics. Euler equations, Navier-Stokes would be the higher level, more complete equations. So Reynolds average, Navier-Stokes. We can upload geometries into the software, set it up, run it, and it simulates fluid over something. So CFD is great because it's cheap. You don't have to build a model. You don't have to spend time testing. You just draw it, hit enter, and it's doing the test. It just takes time. This computer has 512 gigs of RAM to work through issues compared to maybe 8 or 16 you'd get on a nice computer at home. It's got just crazy fast and lots of processors. It's got 40 processors that can work in parallel on a problem, as opposed to your quad core or maybe 8 core machines you might have at home. Really good graphics card as well. It can do some good simulation, which is where this thing comes in. It also has a flight simulator on it called X-Plane, which you can buy and run on your home computer. But on this, it's really, really good. And we've got a hang glider built in the simulator, and this is a hang glider control bar with some Arduino connections to the computer. So one of my former students who worked for Nissan at the time designed this for the Red Bull Flugtag competition because his Nissan team built a hang glider, and he built this at Nissan so they could test it in X-Plane. And then when the competition was over, he donated it to my lab. So you can fly a hang glider here with this thing. And you can, in that software, design airplanes, flight test airplanes in the software, which is part of my background. I'm a flight test engineer before I became a professor. And so the flight testing is near and dear to me. You can design flight tests inside this one software, whatever kind of airplane you want to look at. Other little bits and pieces of fluid mechanics / just testing equipment up here. This is a little bitty baby wind tunnel that we have that uses model train smoke. You can set it up on any tabletop and visualize flow through something easy breezy like this. For the propeller testing that we've got going on, this is where we're going. And Danielle, I don't even think you've seen this yet because I haven't pulled them down in a while. So all of my testing right now for the last 3 years has been on small little propellers, the size that I've showed you, that are typical of small drones, quadcopters, or fixed wings, but quadcopters, octocopters are much more common. However, those unmanned systems are getting bigger, and bigger unmanned aircraft are going to be in our airspace in the next decade or two, legally. And so one of the areas where that's going to come in is called urban air mobility, where when you pull your phone out and you go to the Lyft app to call for a ride, and you're looking around, where's my car? You might have to look up and see where's my drone, because they're designing systems now that big drones will drop down, you step in, and without an operator, it will fly you to your chosen destination. So this is what's being worked on actively right now. So urban air mobility. Inside of that also is drone package delivery, which has also happened already in the US on a very small controlled scale, but it's coming more on a big scale. Like you order something on Amazon and a drone comes and drops it at your, or gently places it by your front door, hopefully not drops it. But for the big thing, you stepping into a drone to fly you somewhere, everything's getting bigger. And here are some bigger propellers that are of the size for an unmanned aircraft to fly you and me around. That's what this prop is built for. So it's a carbon fiber blade that's meant to go on a very big electric motor. The big electric motors are in here. And this driven by one of those big electric motors can make, I think, 70 to 80 pounds of thrust. So if you've got 2 of these, you can almost lift one of you, a smaller one of you. For somebody like me, or if you have more than one person, it'll take 4 to 8 of these to lift somebody up. But they're doing that right now. Actually, in other countries, they've already done it. They've already given people some autonomous rides. In other countries in Asia, they've done it. So these are things we will be testing in the future. And in that cardboard box right there that's been opened, you can see some of the aluminum structural members there. That is a force balance that I'll be putting together that is a force balance big enough to handle something like this, to measure thrust for big things. That goes up to 80, 100 pounds of thrust on the force balance. So those are things we'll be working on in this lab, some more fluid mechanics type things. That is pretty much all the big stuff in the lab. Since you're here, and since you guys are very interested in fluid mechanics, you can't get enough of it. Do you have any questions for me? And it could be fluid mechanics, it could be aerospace engineering, flight test engineering, or just general engineering oriented. You're hearing a lot of that good stuff from your professors. But do you have questions for me?
So when you give like the thrust number, like for that prop there, you said 70 to 80, that would just be like no load. That's 70 to 80. Not like if you were to put it in some kind of vehicle, you'd have to take into account like the motor and other things like that that would,
Well, the motor is driving it. So You've got a couple conditions. The biggest condition is what's the airspeed that the whole system is in. So if I've got any prop, like that little prop on that thrust stand, if I've got it mounted there like it is right now, and I just spin it up, well, first it's a function of RPM,
Right.
so I know what RPM I'm set, but this would be a static thrust number.
Okay.
This would be similar to a quadcopter just hovering.
Right.
It's static, it's not moving, right? It's drawing air through it, but overall the system is not moving. V infinity is 0 for it.
Okay.
But if we've got something like a fixed wing airplane, you've got a propeller spinning and it's moving through the atmosphere.
Okay.
Then its thrust is a function of its airspeed as well.
Gotcha.
So right now we're doing static testing for static thrust for something hovering like a quadcopter. If we wanted to measure thrust for something moving, we'd have to install it in a wind tunnel
Okay.
or do flight testing.
So if it's moving, does that help or hurt your number?
It hurts thrust.
Okay.
If you look at thrust from a propeller, it's greatest when it's not moving, static. When you start moving it,
That's the
its
issue.
thrust drops fairly linearly as well with
Okay.
airspeed.
Interesting.
How much do you guys get into jet propulsion, or do y'all at all?
The courses that I teach here in the department are the math and physics-based, engineering-oriented type courses that are taught at a level that everybody in the department should be able to pick it up, because we got a lot of non-engineering technical people in the department. The majority are non-technical. But in my freshman course, I teach propulsion topics. So we talk about how reciprocating engines work. We talk about how turbine engines work to include turbofan and turbojet engines, ramjets, scramjets, rockets. We give an intro to that. In my senior level class, aircraft performance, we talk about what those propulsive systems do to the overall performance of an airplane.
If we wanted to take a class or like about some of that stuff, what would you recommend?
Sign up.
Well, for the freshman course or the
So you can start off, maybe Theory of Flight is a good one, Aero 1020, because it orients you to the vocabulary within aviation or aerospace and gives you introductions to those topics. Now, many of which you would already be familiar with. The physics, you should already be well versed in. But as it relates to aviation, that's what that course would start you in. But you could skip that one if you wanted to and jump right into aerodynamics. Aerodynamics you have to have, and that's a junior level class, Aero 3440. You need calculus, which you guys are well beyond that by now, I'm sure, and you need physics. That's it. As long as you've got those two things, you can sign up for aerodynamics.
does it matter algebra or calculus based?
Well, I mean, I just have the base level calculus because pilots take that class as well, non-engineers. So math 1810 is the lowest math I'll allow people to come in with. But for all of you, math 1910 is what you would have had. So if you've had your calculus and your physics, you can get in.
Okay.
And be fine. I do a lot of math and physics review in the class, so even if you're not comfy, you will be comfy as we move on. But that course, to be honest, it's packed every semester and there are waiting lists every semester. So as soon as registration hits, if you're considering adding a course like that in, you better do it as soon as you can. But I teach it every semester, fall, spring, and twice in the summer. And then aircraft performance at the senior level, you got to do aerodynamics before you can do aircraft performance, prerequisite wise. That'd be a good one as well. That's a good way for you guys in mechatronics to give yourself just a little bit of a broadening experience, see what aerospace engineering might look like. What else?
I have a couple questions. Is there any benefits to modifying the propellers that you have versus just designing existing, redesigning them and actually making brand new ones?
Well, the benefit is that so many people are using the ones that are already out there now. If you can come up with an easily applied modification to a propeller, there's a pretty big market for that because everybody already has the existing prop. So if you can come up with a way to modify, it's like an aftermarket car sort of thing. If you can come up with an aftermarket exhaust like a Kropovich, that's a big market because you can sell to everybody who wants that, who already has the stock.
Gotcha.
Designing small props is difficult, especially using things like 3D printers because the smoothness of the surface is pretty important. And 3D printers, the resolution is still not good enough to make it smooth enough. You'd have to do some sort of surface treatment after the fact. Yeah, you can design good ones, but that little quiet prop over there,
Okay.
that is a nicely designed prop.
Okay.
I don't know that I could make many improvements above and beyond that in the design. And they've got the economies of scale with DJI
Yeah.
that they're making tons of them.
Okay.
But if I can modify theirs with an easily applied modification
Mhm.
and get a sound improvement, that'd be a big deal. And you can't build what we're doing for a modification.
Yeah.
The modifications are adding maybe soft, flexible materials to it.
Okay.
It'd be harder to build that in one
Yeah.
piece. So those modifications aren't easily like stamped out of or poured into a mold or something.
Yeah.
You gotta apply it after the fact.
Okay.
How much more quiet is that one? Like, does it make a huge difference? Cause I have a drone and it's
Yeah.
loud as all get out.
Yeah,
Yeah, I mean,
so
you hear yourself think.
That's a
It's
Phantom
crazy.
4 Pro Plus, which is the pretty common, it's the ubiquitous
Sure,
drone. The old props, we're talking about, and if you're hovering it, it's really close to you, 80, 90 decibels,
Mhm.
which is loud, too loud to be around it very long. Actually, if you've got an Apple Watch, the newest iOS came out with a sound pressure level, sound pressure level device or app on here, and it will alert you when you're in loud environments saying, hey, it's dangerous for you to be in this environment for a certain amount of time. And it constantly tells me, like if I'm riding my motorcycle or if my hand's out of the window of a car, this environment's too loud. It's over 90 decibels. So they can be over 90 decibels if they're close to you. The further away they are, of course, it damps it a little bit, and so it gets quieter. What DJI advertises for that quiet prop is that it's 4 decibels quieter than the original, which that is a significant difference with when you talk about decibels. But what we've done in our testing earlier this year, we verified, yeah, it is 4 decibels quieter, but it's only when it's 4 feet away from you. If you even get it 10 feet away from you, the difference between the old prop and the new prop shrinks down to maybe 2 decibels. And the further away you get, the closer and closer and closer they get to the same sound pressure level. So it's only like right up in your business when it gives you that high noise reduction. When it gets further away, like it's normally gonna